Then let's get started. Welcome to Practical Course 5 on Flexible Human AI Interaction here at the IK2022. Yep. Before I even get started, I want to say that this is a shortened sort of try and pull out some interesting elements modularization of a much larger lecture series that I developed for Newcastle University and ran there in 2021 last time. And it also builds on a lot of existing sources. I will shortly paste a link in the chat to the lecture slides as well. So you can look at these links, whatever you see, if you see something interesting. And later on, we'll have some practical elements, of course. And for these, you can also use the PDF document to execute the links. And because of this being a lecture before, some of the elements I will go through really quite quickly to try and get us to the practical things. Yeah, just so you're aware. But if you're completely lost or people really are not understanding something, feel free to step up and ask a question. You can step on the podium. I will see you approach. Or you can write a message to me, a private message, and I will try and keep a lookout for these and answer questions on the go if they are smaller things. And other than that, there will be time to discuss the content later in the session as well. So for myself, I'm Jan Smeddinck. For my background, I did a PhD in computer science, digital media at the University of Bremen in Germany. And I then did some postdoc time there before doing some postdoc time in the US. And then I worked as a lecturer at Newcastle University with a specialization in digital health, led a research group there. And I then moved to Austria, and I'm the principal investigator for digital interventions and data analytics at the Ludwig Boltzmann Institute for Digital Health and Prevention in Salzburg, where I'm also currently the co-director. Anyway, that's just sort of a little bit of a background on my journey. I have done a lot of work on interacting with adaptable and adaptive systems, in particular in the context of digital health, and there machine learning has played a role for quite some time. And of course, most recently, interacting with AI technologies is becoming more important in this space as well. So what's the motivation for this course? I think you're all quite aware that machine learning and AI technologies are becoming quite ubiquitous. They're really starting to be everywhere, be that as your translation tools or various image recognition applications or many other things, really, automatic tagging or recommendation systems that you interact with, or that we all interact with on a day-to-day basis. And this has an impact throughout society. And it's getting to the point where we're seeing this diversification or segmentation of activities in machine learning and AI. So not everyone is working on the bare bones foundations any longer. It's getting rare, actually, that you get people who cover the very, very foundational methods development all the way up to various applications. It's just too large. So we see this specialization that has happened before. For example, when human-computer interaction sort of started branching off from computer science, or came together from computer science and psychology as a specialist area that was required because of the large world ubiquitous impact that computing technologies were starting to have. As we will discuss in a later session quite explicitly, there's also a notable break with established usability and user experience paradigms when you look at human AI interaction, or how we interact with AI systems. And I will comment on that further, but it's really important to recognize. The sort of wide availability, and we will get some examples later, of AI and machine learning tools, and them also becoming wrapped up in a way that they are way easier to use, is getting us to a point where really designers are starting to understand machine learning and AI tools and methods as a new fabric, as a new material type of tools to work with. And that's also really interesting and something important. And we need to think about how these tools work and are encapsulated and described so that things go well. We can argue also that we're on the verge of a democratization of these technologies, but currently it's probably still valid to say that the big players, your Facebook, Amazon, Google, and so on, sort of still lead in many regards. So those who hold a lot of data, and we'll also comment on that later. So when we are seeing this abstraction and specializations around machine learning and AI, likewise to the fact that not everyone knows how chips are constructed, but we still do a lot of things with using them. And likewise, we don't need to have everybody look at and understand the foundations of machine learning and AI in order to be able to use them these days. And that's a really important observation. That means we need to start thinking about human-AI interaction more explicitly. So this type of expert knowledge is no longer required to produce something like this within the space of, say, 10 minutes. Yeah, this is just an example of code from a Google Colab notebook that you can run later and produce your own sort of target image driver video deep fake style productions. This is very easy to do these things these days. And of course, there are now even consumer-oriented tools that everyone can use within seconds, no learning required. Traditionally, one could say most artificial intelligence machine learning courses have been quite disconnected from the real world problems that are now being tackled with these technologies, at least to a large degree. And that was understandable, and it still is. There's a justification for these courses, but it's no longer the right thing for everyone with this diversification that we're seeing, I argue at least. Most AI and ML courses used to consider user interfaces or the impact on humans as an afterthought, and it really focuses on the methods. And that's good, but it's also a problem. And not sure you may have seen this or many other elements before, but this is one of the famous examples, the gender shades study by Bulamwini and Gebru from 2018, which was really a seminal study from MIT showing that different facial gender classification systems had really different error rates depending on individuals being lighter skinned or darker skinned. And this is an example, of course, of biases in AI and machine learning systems, and it's a real big problem, resulting usually from biases in the data sets already, sometimes from the processing methods or the applied methods as well. But it's a big issue, just as one example. Another one are the various applications that are arising now out of these technologies. Of course, one of the most notable ones being deepfakes, where we can do impressive and fun things with them, but they also have grave implications. Like what I'm hinting at here is that, politicians can be made to say things that they never said or do things that they never did. And we can also expect that these can and will be interactive. So you might be interacting with somebody in the video chat, and they are not who they appear to be. So these things also, of course, have grave implications. Right. Just checking out the poll that was posted there in the main chat. So this course will have 4 sessions. Today we will focus on this sort of ubiquitous nature of machine learning and AI and why we need human-AI interaction in the first place. I also cover a little bit the history and foundations, and when we do some fun interaction. Session 2, we will look into this sort of balance and trade-off between automation and control, and also try and establish some terminology about human-AI interaction, human-AI user experience, and sort of related terms and approaches. And in a following session, we will go into a little bit more detail about these aspects of bias that I just mentioned, together with fairness, and also briefly bring up explainability and relatability and other exability aspects of AI systems. So this sort of links to the evening lecture, if you've seen that yesterday, by Tarek Bezold. And there will be a practical example around explainability in that session. And session 4 will be mental models, embodied interaction, and sort of a future outlook of where are we going with human AI interaction. Again, there are practical elements in each session with this. What I shifted to this online format, so it's a little bit more condensed than it would have otherwise been. So it's about half lecture, half practical, and I will try and stick with this as best as possible. Today will probably be a little bit more lecture, but we'll see. It's also not a basic introduction to machine learning and AI. I will really just cover the super bare bones foundations, which many of you will be familiar with. So I'll try and be quick, but just to cover some basics, and then really think about the interaction aspect of AI systems and machine learning systems. So what does it mean for humans to interact with them, and how do we understand that? How can we make systems that will have a chance to work well in this context? So we'll really try and highlight that in the larger lecture and module, where these materials to a large degree stem from. There is also a foundational introduction to machine learning and AI baked into it. Okay, good. So let's start with the actual content here for this session. I will just briefly, coarsely run through a history of AI and ML, together with hints at how human-computer interaction developed in parallel and how these started playing together quite early. But now we see a big emphasis on these things around human-AI interaction. So rough history of AI, you may have heard this before. We have this timeline with AI springs and AI winters. So there's of course a long history. Mankind has always, or humankind has always been fascinated with the idea of artificial life. This is visible in old myths like the golem. It's in stories like Frankenstein. It carries on to current times in much more modern iterations, like you see a screenshot here from the recent movie Ex Machina. Even early on, before AI systems were really a thing, various people started thinking about how it might be for humans to interact with autonomous systems. So we have, of course, the famous robot laws by Asimov. And again, I'm skipping over things here. This is really just to point out some things, but you could say this is very, very early human AI interaction type thoughts concerning the safety of systems. Of course, as one sort of key point in the development and the history of AI, we have the development of the perceptron in 1958 by Frank Rosenblatt, was made specifically to run image recognition for the US Navy, linking photocells with a dedicated perceptron machine. But what happened quite soon with these developments that showed some type of automation successes was that building on comments by the originators, sort of public debate on these technologies quickly derailed, as it tends to. So we see here a quote from the New York Times, 1958, describing the perceptron as the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, and reproduce itself and be conscious of its existence. And what this is pertaining to is this big issue of don't promise what you can't keep, right? We see similar quotes throughout history here. Machines will be capable within 20 years of doing any work a man can do. Prediction by Herbert Simon in 1965, or Minsky as a famous representative of this early school of AI researchers. From 3 to 8 years, we will have a machine with the general intelligence of an average human being. Of course, that didn't really come to fruition, and this is the basic idea of hype cycles, where a lot of excitement builds, but then the technology can't quite speak to the expectations that have been raised, so there's a through of disillusionment. However, if the technology was worthwhile, as is the case with machine learning and AI technologies, of course, we will see sort of a movement pick up again. And this is then related to how the world got excited about AI, then meeting breaking points multiple times. So with the perceptron, the breaking point was actually Minsky and Papert publishing a book on perceptrons, where they really tried to argue for a rule-based approach instead. And there was a key argument around how perceptrons cannot handle even an XOR operator, which is technically not true if you allow multi-layer perceptrons. There's a solution for that here, but again, that's not the purpose of this lecture. It was known at the time, but somehow still funding for neural networks research was greatly reduced. There were some parallel developments and reports in the UK here at play as well. But Rosenblatt, as the inventor of the perceptron, died before actually seeing neural nets revindicated and revived later on. It's just interesting to consider that in parallel, there was the whole discipline of HCI really started to shape up. It was only called that from the 1980s. Before then, it was human factors. But there's this decisive moment with Douglas Engelbart running the mother of all demos, in which he already sort of posed computing technologies with the purpose of augmenting the human intellect. Now, he was much more about interaction design, or the early ideas behind it. How do we make technologies so that they just work very efficiently so we can do amazing things with them? But from the very beginning, this idea of augmenting the human intellect was in there. And this is an important consideration that we will pick back up on a few times. So if we think about artificial intelligence developments as the aim of building some potentially human-like intelligence, or intelligence for some specific types of tasks, then to contrast that, there's also the idea of intelligent augmentation or amplification, where computing machines can do routine work and prepare the way for insight, decisions in technical and scientific thinking. This is a Licklider definition, or later on Eric Horvitz saying an elegant combination of reasoning machinery and direct manipulation. So these even in these early research contributions, there was a strong idea of linking the automation potential of the computer with also ideas of direct manipulation, giving the right tools to exercise with a lot of control directly what we as humans want quite efficiently. And this has been a sort of a back and forth that carries through history as well. Yeah, I want to cut this a little bit short, but we then saw a second wave of AI around symbolic AI. So this idea that formal logic systems can represent intelligent action, which sort of culminated in Lisp machines. And it's beautiful and fun, and you can have some really nice successes with it, doing some math proofs, searching logic spaces. And even in natural language processing, there were some impressive advances at the time. But there are strong limitations in scalability, because somebody needs to write these rules. And we saw that in expert systems, it's quite possible to write rule-based expert systems that succeed in small, very well-controlled scenarios. But it's really, really difficult to get them to work in a generalizable fashion. So this sort of issue of combinatorial explosion, or the curse of common sense, what seems like simple rules that we follow in our everyday lives as intelligent actions really becomes devilishly complicated if you try and implement it. And if you have time, you can click through the lecture slides. There's a fun video of robots failing here as an example of what that leads to. So anyway, there was this second disillusion, second AI winter, and from the 1990s to the 2000s, AI sort of went undercover. It wasn't really a thing to say I'm an AI researcher. This was actually quite evident even into my early days at IK. 2010-ish was when the machine learning boom then started, though, coming up. Because in parallel, we did see many advances in computer science. It's interesting, there's a co-evolution with video games and the technologies, sort of graphics card evolution, for example, that they enabled. So machine learning was a sort of etched out as an individual field that wasn't AI, but sort of, and it was legitimate to work on that. And sort of with the general public going online and the development of the internet really allowing lots of data to be gathered and exchanged, data availability became better. There was concepts of linked data and open data. And that really allowed for a boom in machine learning to together with the, of course, the advances in semiconductor development, much more so than methods development actually really at the time. But there were some methods breakthroughs, of course, too. And around 2010 or so, we suddenly saw many practical applications in much advanced natural language translation, things like that. So neural networks became much more practical at scale, and many earlier interventions like backpropagation, for example, were suddenly rediscovered and had a big breakthrough. Massive funding was back, is still back. And we are seeing much more combinations of research and real-world deployments, which is this whole point of ubiquity that I mentioned earlier, which is really a shift, a change. It's unlike, I would argue, earlier sort of AI winters and springs. So suddenly it's okay again to say you're doing AI. And at the same time, human-computer interaction has moved from an early focus on making systems efficient easy to use to user experience, right? Focusing on what does it do to people? How does it feel to use systems? And with the sudden ubiquity of machine learning and AI systems and their widespread use, this little bit of a neglect for understandable reasons earlier on user-centered aspects became quite obvious, with some of the examples already hinted to, and we'll cover that a little bit more later on as well. But this is sort of the roots for contemporary drive and a lot of interest now and activity in this new developing sub-area, somewhere between computer science, AI, machine learning, and human-computer interaction design, and so forth. There's this fusion now looking at human-AI interaction. This was a very, very coarse introduction, of course. I have a couple of links to interesting materials to read up more on this if you're interested. To recapitulate the timeline, there's this history of AI springs and winters, and we have now seen a quite long spring. It's actually a valid question to ask where we're headed. So if you look at some Google Trends, I'm not sure if I'm not looking for the right replacement terms of things that are now more relevant, but you can actually do this with deep learning, machine learning, AI, some other aspects. You will see recently, actually, a little bit of a decline again. So the question whether winter is coming is a valid one. I don't know. I would argue we have now sort of seen the iPhone moment of AI and machine learning. So my bet would be it's not going away, but maybe just a little bit less temporary excitement. But we will see. So before we go into the practical session, I want to just cover, as I said, some very basic concepts. Again, I will be quick with this, but if you write me, because I'm looking at slides, if you write me a personal message in the chat, I will hear it and I will answer it in case I'm going too quickly. Right, machine learning in and of itself, there's this famous definition by Mitchell: a computer program is said to learn from experience E with respect to some class of task T and performance of measure P if its performance at task T as measured by P improves with experience E. So that is just trying to find an expression for what is learning in a machine system. So basically saying it's a machine that is able to improve based on past experience without an explicit sort of rule or programming on how to improve each time. Of course, implicitly, that is the case with things like backpropagation. But right, and there's the standard machine learning pattern. Then, so if we pull out these letters here in Mitchell's definition, experience usually is data in the systems, like training data or feedback data on the system performance. tasks are very often prediction, maybe classification as well, recommendations, some natural language generation, etc. And then performance is usually measured in accuracy, and then we have additional measures, of course, and quite a lot. But as a general simplification, accuracy is a key outcome. And machine learning is, of course, a rapidly developing area, but roughly speaking, it was surprisingly difficult to find a good overview, because I don't agree with this one being a good classification system. But anyway, just to get the general idea, we have these three types of machine learning: supervised, unsupervised, and reinforcement learning. They do different things, and there are lots of various applications we can do with them. But here I'm already not happy with how the applications are linked to one type, which is clearly not the case. But anyway, just to give you the idea, it's a lot of different things. And then for artificial intelligence itself, there's Russell and Norvik's definition: the designing and building of intelligent agents that receive percepts from the environment and take actions that affect that environment. Interesting take, as always, with definitions. They are tricky. I mean, if you wanted to be radical, you could argue that an automatic door fulfills this definition of artificial intelligence. So clearly some more nuanced notion of intelligence is necessary, maybe around properties and capabilities such as learning, reasoning, problem solving. We can consider language, and also detail what perception means a little bit more than just saying percepts. But so maybe we add to this definition intelligence the ability to learn and solve problems. So there's a learning aspect in that now, which is, I think, quite important. Without going into much further detail, a very prominent method, of course, in machine learning and artificial intelligence these days are neural networks, and there are many different types. We just briefly covered the perceptron earlier, and these have, of course, since developed into many different structures, and this is an area of ongoing research. What's becoming more important recently, one might argue, beyond the individual nature of how networks are composed or their general architecture of a network in itself, is the sort of meta-system architectures. And we see that a lot with recent sort of very ambitious language models, for example, where it's a lot about memory architectures across different system components suddenly. And yeah, the famous term, of course, in recent years, deep learning, really typically an application of artificial neural networks where we just say deep is somehow 10 or more layers, was the famous definition by Ilya Sutskever in his IK talk quite a few years back. But generally the idea is that these networks quite dynamically learn to progressively extract higher level features from raw input. So that's just to cover the most basic understanding. And of course, it's important to keep in mind that there are a lot of arguably artificial intelligence methods that are not machine learning, like search-based approaches such as the A-star algorithm. A lot of the techniques used in computer games. There are expert systems, as we mentioned earlier. Then, for example, some of the magic that search engines work is, or at least used to be, not machine learning. And then, of course, for language processing, lots of machine learning these days, but also, especially in the past, there used to be lots of rule or grammar-based systems. But many projects, as it says here, are also somewhere in between. So yeah, just to say that. Now let's return to the standard supervised machine learning pattern, where you have some data set, usually derived from the real world. The basic idea is there are various methods you can use to train a model. And you section out some data as a validation data set to test the model, and then you do some documentation of your performance. Let's not get into details here about validation and test data sets, but that's the general idea. So yeah, this is of course yeah, just a rough structure. It's important to recognize because, yeah, depending on where you're coming from, this is of course nothing new at all, but it's important to consider the aim of what you're trying to do. Is it a typical common task is regression, where you try to predict a specific value, like for example, the specific temperature tomorrow, or whether you want to classify, like, is it rather going to be hot or cold tomorrow? And then depending on what you're intending to do, we have different methods at our disposal. So for clustering, there's, of course, the classic method of k-means. This is an example of unsupervised learning. And yeah, if you look at machine learning approaches and tasks, you could roughly summarize for supervised learning with the standard pattern I just showed. This is often used for classification tasks or regression, such as the prediction we just looked at. Unsupervised learning is very often used for clustering or representation learning. And there's, of course, reinforcement learning, which you could argue is a modulation of supervised learning. But anyway, it's really good at learning complex task action sequences. And the idea in the architecture, of course, with supervised learning, you have an input, the method produces an output, and then you have a way to clearly validate whether there was an error in the prediction output, and then you can improve your model. Unsupervised learning, typically there is no such feedback cycle. With reinforcement learning, there is, but there's, of course, some sort of a scoring mechanism at work to assess the performance, a fitness function, something like that. And there's typically a lot of intelligence going into that. Again, if you have time, you want to look at a fun video of a classic reinforcement learning paper. If you haven't seen it, I recommend. These running figures are always fun to look at. Just to say, it's really impressive how reinforcement learning systems can pick up complex behavior patterns. Yeah, and you then want to, in the standard machine learning pattern, you want to be able to say, how is my system performing? At the most basic level, this is captured as the accuracy of the system. So you can simply see how many of the system predictions were correct as compared to the number of total predictions it made. And of course, with this, you can then separate in true positives, true negatives, as opposed to false positives and false negatives with the system predictions. And this is really important. This has real-world consequences, and it's a good way, actually, to weigh potential impacts of an AI system or a machine learning system when you're designing it, is to ask yourself, what is the impact of a true positive or a false positive or a false negative or a true negative outcome of the system in its real-world use, right? And this can be the direct impact of the outcome, or it can be indirect impacts that one might not expect. So here's an example. I think this was from the Uber accident case. It was from this famous Uber crash with a fatality, I think, in that case, right? And it's a little bit of the backstory here, but the key point is the car actually recognized, I think it was a cyclist, and there was an auto brake event triggered, but there was an engineer in the car actually overriding the trigger because they were used to the system overreacting, so sending false positives, yeah, and so they stopped the system. So here you see a quite critical or issue with sort of an outcome related to being too worried about false positives, so having a bad false positive rate in a system and that not being considered sufficiently enough, apparently. Right. Of course, we have many different application areas. So systems get widely used in computer vision, natural language processing, recommender systems, and we will get to that in a later session when we talk about decision support and use that as a critical case in, as a sort of a design critique exercise. And yeah, basically, what I want to point out is that we had this development of computing becoming ubiquitous, and we now have a development of machine learning and AI systems as a specific type of computing system becoming ubiquitous. And this means that systems that are much more dynamic than what we're used to, that are potentially learning, that are potentially quite adaptive, are becoming widely available, in particular as online services and mobile apps. And that really means, as I mentioned earlier, they are becoming widely available, commoditized to designers, to developers that are not experts on the underlying methods. Still mostly centralized, but it's a really impressive and fast development. So we're sort of moving from the idea of there's an app for that to there's an agent for that, and that changes how we do interaction design. That changes how we think about human-computer interaction. When we evaluate learning systems and how they work, I just mentioned we want to ask how often is a prediction wrong, but we also want to understand how is the prediction wrong and what is the cost of a wrong prediction. It's also interesting to ask whether the cost varies by the type of prediction that was wrong in the system and how we can minimize such costs. And then when we expand the idea of human AI interaction to also look at human AI user experience, then we want to look into concepts such as misunderstandings, frustration, regret. And we'll do that in session 2 and 4 a little bit more. Right, but this is meant to be quite practical as well. So now I need to switch my view a little bit and see who's here and where. So we will try and do a little bit of a practical exercise if you're still awake in there. In this room, there are plenty of seating spaces. And if you walk through some of the areas where you see chairs here in the room, then you will notice if you do that, then the immediately surrounding group of chairs gets highlighted. That way you can quite easily form groups, or you can run into the corner and flee if you don't want to participate in the interaction, but I highly suggest it. So you can quite easily form groups by moving into one or the other group of chairs. And what I suggest we do is just to get a sort of a warm up is to look at a couple of AI systems. I shared the slides online, so you can find these links to click at, but I will also drop a link to the slides in the chat in a second again on another place that doesn't require a password for now, so you can open the slide and use the links. So I picked out 5 quite different systems that are AI and ML systems, or are systems that have AI and ML components. And I will suggest in a minute to form groups and look at these systems and play around with 2 or 3 of them, not all of them, but play around with 2 or 3 of them of your choosing. And then to have a little bit of a group discussion with, I would suggest groups of maybe, 2 to 4 to look at these systems and really think about how users interact with them. So primarily in this case, you, right? How do you interact with these systems? How are they posed and constructed? So how was it for you to use these systems? Is it fun? Is it interesting? Are they easy to use? Are they difficult to use? Likewise, how are they different if you manage to look at 2 or 3 of them? And what value do they deliver? Do they solve a problem? And also, who are they good for? And maybe for fun, to try and make some links, just to toss that in. Are they somehow flexible, or do they offer flexibility? So these are the questions, and these are the systems. So the system, with a cat drawing. There were some others there too about shoes and buildings and whatnot. I think there was an easy interaction for people to find into, even though you maybe had to wait for the model to load on the website. But some liked it because it's interesting to experiment with, like what happens if I just add one more line here or one more line there. So it's clearly a machine learning system that is trained on some image data, and it does some edge detection too, and then based on edges it's given, it can then be used to produce. But the way the interaction is done here, I think you can put this on quite a few dimensions. But if you think about whether this is rather for a consumer or rather for a machine learner or somebody who cares about building development models, this one is probably somewhere in between. It's more like a play around thing for people curious about machine learning and interaction, I would say. Because you can still understand quite a bit about the system. It might get you curious. It's wrapped up in a way that it's certainly easy to use and get into, but it doesn't give you immediate access to interact with its code, for example. This is what's possible in the Colab notebook example. If you clicked at that and managed to run through it, I saw one group at least producing a deepfake in this session, a deepfake Mona Lisa driven by Donald Trump video. So that one is still very easy to use, I would argue, but it actually gives you the possibility to interact at least with the way the model is used. It doesn't actually give you the model composition, but it's certainly much more technical. And then there is the very consumer-facing application of a machine learning model, the blob opera, if you looked at that silliness. It's even artistic or playful in the way it's wrapped up, but there's a machine learning model in it that has learned how human singers harmonize in quite complex situations, and it can exert that to dynamics where the users decide, what lead note to sing, and the others will follow. And of course, this is one of these examples of these systems just becoming ubiquitous and being everywhere. And in this case, it's certainly not an example, not an issue that it does a lot of wonderful automation, this system. But it's also, as one group commented, quite a black box. So we have no idea what's happening exactly there or why something's happening exactly. And we also can't stop the system and interrogate it or try and understand why or what's happening. So this is this trade-off between automation and control that you can already see in these systems. They all sit somewhere else on that scale, and that's one of the key topics of the next session that we will look into. That's always one of the key decisions when you deal with machine learning and AI systems, is how far do you automate and how much control does the user have? And how do you figure out what is good to automate and what is good to leave to user control, or how to let them decide? There are many, many things to consider with that. And with that, maybe we close this session. But I'll stick around for a few minutes if there's any curious insights you would not want to discuss in the larger group, but then maybe in a smaller group. Other than that, I would hope to see you in 2 days. And if you play around with these systems a little bit more, we can have a few minutes in the beginning next time if there are further thoughts. So thanks for joining for today.